Hello, my name is Patrick Young. I'm presenting lab number 2 for Physics 2211, where we explore the motion with gravitational and drag forces. So our big concepts here are Newton's second law, with a net force not equal to zero. This can be written as V final equals V initial plus F net over m times delta t. An object that falls to the ground has a non-constant velocity, and this indicates an F net that is not equal to zero. So we must explore what forces are acting on the object. Well, we have the force of gravity or the weight force, which is the force between any two objects with mass. We calculate this on Earth by multiplying the gravitational constant, aka 9.8, by the object's mass. And then we have the drag force. This is described as the force opposite to any object in motion. We calculate this using the equation b times velocity squared, where b is representative of a proportionality constant dependent on the airflow around the object. It also begins to explore terminal velocity, which is the point where an object in free fall's gravitational force is equal to the force of drag. So in this video, I analyzed a solo cup and tracker. As you can see here, I set my axes right here, where the origin being at the center of the solo cup, and my calibration stick to 0.117 meters, which is the standard height of a solo cup. So if we forward it in here, we can watch my tracker video as I drop the cup. As we see these red spaces over on the right, we have our t, time versus position for y. And then we see as the cup drops, the space between the dots becomes larger and larger as it accelerates closer to Earth. So then we jump into GlowScript code. Right here we have g equal to 9.8, which is our gravitational constant on Earth. Then we have our time parameters, which is we derive from our tracker video and tracker data. And then we have our Fnet statement where we set the weight force equal to negative ball m times our constant g times the unit vector j hat. Then we set our Fnet equal to w. Also, we have to use the velocity update formula, which is also known as Newton's second law. So right here we have our GlowScript model, and I'm going to run it. And we see that our computational model follows around the same path as our experimental model. And so here we just compare with just the gravitational force our experimental versus computational model. We can see our experimental data finished at a position higher than our computational model predicted. This is because we did not factor in drag force. So our computational model would finish lower on the y position because it believed that there was no drag force. So now we adjust for drag force. And we see in our statement down here, we set the force of drag equal to negative b times the magnitude of the ball velocity squared times the negative unit vector j hat. And then for our force of net, we add the weight force and the force of drag. And we keep the ball velocity update formula the same because that's a fundamental concept of physics. So when I run this simulation, the orange arrow represents the force of gravity, and the blue arrow represents the force of drag, and this becomes greater as the ball's velocity increases. This is due to the direct relationship between the drag force and velocity, as we modeled with b times v squared. So here we plot all three against each other, and we can see that the brown and orange is our experimental and our computational model with drag factored into account. And our down here, our reddish orange is our just our computational data with no drag force into account. And we can see that when we added in drag force to our GlowScript code, it revealed a much more accurate model representing the real world. So now we got to answer some questions. Which models, if any, predicted terminal velocity? Well, neither model had a ball approaching terminal velocity. We can look at the slopes of the position graphs and compare these and see that they are not flat and they are still increasing negatively. So also we have to answer the second question. What happens if the initial velocity was greater than zero? So the terminal velocity in this case would be the same. The terminal velocity is not dependent on initial velocity. Instead, terminal velocity is the point where the force of drag is equal to the force of gravity, and therefore our acceleration is equal to zero. As the model shows, the v versus t for the ball with initial velocity and experimental values, there is no real difference. Alright, that's all. Thank you for watching. This has been Patrick Young for Physics Lab number 2, 2211.